All right, so I gotta say, it feels a little bit strange to give a talk on CRDTs, after we've heard, from the people who actually wrote the original papers, potentially, right here in the audience today. But, I'm gonna do my best. I hope you'll find this interesting and useful. And, before I begin, I just wanted to kind of take 2 seconds to say, big thank you to the organizers of Agenda Beach. It's been an amazing 2 days. And just being here on stage in person again after such a long time is just fantastic, so thank you. All right, so let's begin. Title of my talk is Synchronizing State Across a Billion Devices, a CRDT Tale. And we've already heard some amazing talks on the topic. Yesterday we had Nuno and Carlos, and today we had Peter, a few others. And since we like him so much, here's another one. And we're going to be seeing how this is from a slightly different angle. We're going to be talking about state, state in the context of a distributed system, and then we're going to be talking about maths. I know we're thinking, it's late in the day, but it's really light, so stay with me. And it's going to be some specific kind of maths, and we're going to be seeing how the properties of some kind of structure allow us to create systems that are extremely elegant and simple and easy to reason about. Before we get to the core representation, I just wanted to say a few words on who I am and why I decided to talk about this topic. So my name is Marco. You can find me on Twitter at this username with the underscore at the beginning. And I work for a company called Permutive. I even have Permutive socks on today, so it's really committed to the brand. We're about 200 people in the UK, US, and Europe. And to explain what we do, I like to use an example. I find that's usually the best way to kind of illustrate the mission that we have as a company. So I have to buy a new dishwasher, right? My old one broke. I need to get a new one. So I get on my phone. I make a quick Google search, Amazon search, whatever, and then find whatever dishwasher I want to buy. And then, a few days later, my brother, who doesn't even live with me, starts seeing ads of dishwashers on his Facebook, right? And that's not very good, right? That's not something you want to have. And it's also something that probably happened to many people in this room as well, right? It's quite a common problem. Now, what we try to do at Permutive is to fix this situation, fix this whole mess. Remove that if element of online advertising, because advertising isn't necessarily evil per se. It's not like a bad thing necessarily. It can even be useful. If I'm a consumer, I want to buy something, I want to purchase a product, I want to know what kind of options I have available and I want to see how they compare to each other. And what's not okay is the industry that sits behind it at the moment. It's something that doesn't really respect the privacy of the consumer at all. So we try to fix this. We work with the main publishers and advertisers in the UK, US, and Europe, and we offer a more responsible platform, one that generates value for our customers, but at the same time is totally respectful of the privacy of the readers, the consumers. It was important to make this explanation because we're going to need it later on to understand a few things. Also, this is a tech conference, so I have to let you know that we're hiring, of course. We're hiring across the whole of Europe. Generally, we're a totally distributed team. This is the tech stack that we use. If you have a look online, you can find all of the positions. Also happy to chat about it after the talk if you want to know more. Okay, so I want to start the talk with a question. So why? Why talk about this stuff and not something else, right? And this question has to be our starting point, because if we were to start from a nice piece of tech, some nice software, a nice solution, and then from there walk our way back to a problem, that doesn't really work. We have to kind of start from the beginning and understand really what is the problem we want to solve, and once we have that understanding, then we can talk about what we can do to solve that. So really the correct question to ask here is, what's the problem that we want to solve? What do we want to do really? And we can start from here. And this is a screenshot of a portion of the Permutive dashboard, and from here you can create what's called a cohort. And for example, the BBC, who's one of our customers, and I'm totally inventing here, this is not real, just an example, could create a traveler cohort, defined like this. And a cohort is simply a description of a subset of all of the BBC readers, readers who have common properties. In this case, we have 5 pages, so there's this idea of a user visiting a page. 30 days, so we have this idea of a time window, a period of time which we're looking at, and also certain properties. So we're looking for this travel keyword. And the idea of a cohort is really pretty simple, right? We can think of it as a bucket of users. And if we kind of freeze time for a second and we look at the state of our user base, we can see that the 3 cohorts, have different users in them. The first one on the left is 3 users, A, B, and C. The one on the right, there's 2 users, A and D, and the one in the middle, there's nobody in it at the moment. And clearly, it's also possible for a given user, say user A, to be in more than one cohort at a single time. And using the software that we write, the BBC is able to use this cohort on the actual device of the readers. And we've talked a lot about edge computing, in this conference, and this is really what we're leveraging here, like this idea of getting close to where the data is generated. And the interesting thing here is that the data that's used to populate this cohort, so in this case, this idea of a page view with certain properties, is generated on the device itself, and it remains on the device itself. So the information that I am a member of the traveler cohort is on the device and is used there. And it's crucial that this information doesn't really leak out and goes into this perverse system where neither the BBC nor I, as the reader, get any value out of it anymore. And to give you an idea of the scale at which we operate, our SDKs run on about 1 billion devices every month. So this is why we're linking back to that title of the talk, and we're going to see in a second where that need to synchronize state comes from. Let's complicate things a little bit now. So if I'm the BBC, I need to take a sip of water. If I'm the BBC, I probably don't have just one page, right? I have several. And so for the BBC, it would be important that if I visit both pages, my views get synchronized, right? So 2 here, 3 there, and we get to a total of 5. And you could say, hold on a second, we just said that we want to respect the privacy of the user, how does this work, right? And that's a fair question. And there's 2 fundamental points that we need to clarify here. The first one is that the BBC doesn't really know who I am. There's no concept of my identity, Marco, to which we associate the idea that I want to buy a new dishwasher. If we do that, that's going to follow me for the next 2 months, even after I buy the dishwasher across the internet. The BBC sees, someone, a reader, we don't know who, a reader who has a temporary label associated with them. So in this case, this idea of a cohort. And even more importantly, the label only really makes sense and has value for the BBC. It's totally opaque and meaningless for the rest of the ecosystem. And the second point is that the communication across the 2 nodes of the system is also totally opaque, right? The state that we're synchronizing only has value and makes sense within the protected context of the BBC. So at this point, if we remove our business classes and we put on the engineering ones that we really like, this becomes a problem of distributed state. And we can think of the system as essentially the Cartesian product of our domains and our devices. And all of the points in this graph are nodes of our system, and they all have their own very little version of what they think they see to the universe is, right? And it's usually a pretty reduced version of the state, because each node only saw a small fraction of what happened in the universe, right? But nonetheless, each node has its own local copy of the state. And these nodes, they talk to each other, they communicate, they exchange information, they keep each other up to date in terms of what they've seen happen in the universe. And keep in mind, these arrows don't really represent TCP connections. They're just some mechanism to propagate information from one node to another. It doesn't really matter exactly what it is, some kind of propagation mechanism. What we can do now is we can fix a particular user, a reader of the BBC in the universe, for example, me, and we pick the event that we want to monitor. For example, it could be page views. And once we do that, we can create this table, right? Which is essentially a subset of the system that concerns my devices, so it could be my laptop and my phone, and then the domains that I visit. And also we're fixing the event that we want to look at, so page views. And one by one, the different nodes in the system, so we have 4, they start to see events happen in the universe. So we could get 3 pages in this node, 1 here, 4 in this other node, and finally 2 here. And the nodes are not talking to each other yet. They don't even know that other nodes exist in the universe, right? They're totally independent. And if we remember the cohort definition that we used a few slides ago, we wanted to have 5 pages to enter this cohort, right? And each node right now taken individually doesn't really have that, right? We had at most 4 for one of the nodes, and clearly this isn't very good, right? We want to do a little bit better than that. What we want is for each node to have a slightly more comprehensive picture of the universe, right? We want a way for each node to keep track of what happened on some of the other nodes, not just myself, like the nodes that we're interested in, meaning that we want the nodes to be able to talk to each other. And well, they can do that, right? They can we can have some kind of propagation mechanism that takes care of sending an update from one node to all of the other ones. And then we get to this situation. All of the nodes agree on what the overall state is. There's no inconsistencies. There's like a total of 10 for all the nodes, and they all agree it's all good and happy, right? Yes, this is nice. And now let's say that the node on the top right increases its state by 2. And remember that we're simply counting pages here. So it increases state by 2, and it kind of communicates this update to the other nodes. And I'm only drawing one arrow here from top right to top left, but you can imagine that this is actually sent to all of the other nodes in the system. So it says, hey, +2. And the receiving node says, okay, I got you. I'll increase my local copy of your state by 2. So pretty simple so far. Now, what happens if the message doesn't get delivered, right? Maybe it got lost, or maybe we're offline. Maybe they were on a plane or were on the tube. I've lived in London for many years, so I say the tube is not the subway, but you should understand what I mean. You get the idea. So maybe it doesn't get delivered. Or instead, what happens if the message gets delivered twice, right? That's also possible. Maybe we have some kind of retry mechanism in place that retries to send a message based on some conditions, like a timeout or whatever. If that's the case, then we end up with an incorrect picture of the state, right? So one node thinks it's 5, but really is 3. And clearly this doesn't work, right? I mean, it could work. It could work if we never lost any message, and if we managed to do exactly once delivery, which in theory is possible, but do we really want to work with these constraints? Probably not, right? So we need to find something that's a little bit different, something that works a little bit better. So what if instead of sending +2, the node on the top right sends its new updated picture of the state, right? So it's going to say no longer +2, but it's going to say, hey, my new state is 3, right? I had 1 before, and now I got 3. And top left is going to receive this. It's going to receive this update, and is not simply going to add 3 to what it had before, because that would be wrong. It would get to 4. Instead, it's going to take the maximum of what it had before and what it just received. So max of 1 and 3, it's just getting 3. Okay, and that seems to be working. That sounds promising. What happens, if the message doesn't get delivered, right? So it doesn't get there. Well, eventually there's going to be a new message, a new update, but maybe that one also doesn't get delivered. Well, eventually, at some point, there's going to be another one, which eventually gets delivered correctly, so like 7, and the receiving node is going to take this, is going to do its newly learned max operation, and it's going to say, okay, now my state for this node is 7, so max of 1 and 7, and it's going to update its local copy. If we send the update multiple times, maybe we're just like bad programmers, we don't really know how to do this stuff, and we send 7 multiple times. Well, at this point, it doesn't really matter, right? If we do the max of 7 and 7, it's still 7. So we're still in the correct state. So we're not double counting anything. We haven't lost any information. It's still all very nice. And you could say, this is a pretty simple example, but does this idea of taking the max work all of the time? Does it work for all complex cohorts as well? And the answer is that pretty much yes. However, we have to be a little bit more precise and kind of generalize this idea of what it means to take the max for more complex cohorts. Okay, so now we've seen all this. The problem we really have to solve is this one. We need to have a way to count, right? And counting is relatively easy usually. If I have to count how many people are in this room, I can go ahead and do it. And I'm gonna, get to a precise result at the end. In our case, we have to count events that are happening in a totally distributed fashion, right? All of the actors that are involved in this counting process at the end have to agree on the final result, right? They need to get to what's called convergence. Okay, and so at this point, we have a pretty clear picture of what the problem is. Now, how do we solve it? This is the interesting part. Obviously, there's no single answer. There's multiple solutions. The one I want to talk about today, which is the one that we use, is this one. So CRDTs, who would have guessed? We've seen this many times at this talk. Let's start from the end of the acronym and kind of walk backwards to understand really what it means. So DT is for data types. This is pretty simple. We're talking about data structures, so pretty clear. No surprises here. Replicated, so this means that we're talking about a system that's distributed in the universe, right? We want to be able to replicate our state, across the nodes of the system. And finally, the C is for conflict-free, so no conflicts. This is the most interesting part and also the most challenging, right? These structures, when we put them together, they converge, right? They converge alone without the need for any other actor in the system to say how they should resolve any inconsistency. And there's a lot of papers online that talk about these things. This one here is from Nuno Perguesa. You can find it online, or maybe go directly to Nuno after the talk, and if you have any questions, go and ask him. And Nuno talks about two fundamental properties. Properties that we get for free, right? We get these properties for free if we respect certain conditions. And the first property is that the nodes of our system can be completely independent. They can operate independently, and there's no need for them to coordinate. In our previous example, the nodes are simply the millions of readers of the BBC multiplied by all of the BBC domains, and all these nodes clearly operate independently. And this is a pretty strong claim, right? Something that's a pretty nice property to have. The second property is that when two nodes have to synchronize, they can do it sort of deterministically. And deterministically in this case simply means that it's not possible to have a conflict. There's no need for a leader to decide which node is right and which node is wrong. The two states can be put together in a way that's clear from the beginning, and everyone agrees with it. And this is probably an even stronger claim than the previous one. And let's look at an example, very simple. So our state is a single bit, 0 or 1, where 1 represents the idea that some event, it doesn't matter what, some event happened. And now let's imagine a system in which every node keeps a local copy of the state. And all nodes begin at 0, nothing happened yet, we haven't seen the events yet. And periodically every node communicates with the other ones to see if anything changed. And at some point, some of the nodes, 1, 2, 10, 100, they observe the event, they see it happen. So they change the local copy of the state from 0 to 1. And then after that, when two nodes talk, when they communicate, well, getting to convergence is trivial at that point, right? Because the state 1 always wins when two nodes communicate. So it doesn't matter the order in which this thing happened, how many nodes observe the event. The rules for convergence are really clear. Once always wins. So if we go back to the original question that we had, the problem here is that we have to be able to count with some pretty tight constraints, in a way that's totally distributed. And every node in the system needs to be able to count independently, at the same time as the other ones. We don't want to have any lock or anything like that. And in a way that, in the end, all of the actors agree on the result. So what we want to achieve is what's normally called strong eventual consistency, right? But here, we're in the real world, and there's many things that can go wrong. There are many things that can not work as intended. And if you think about our system, with all of these decays that operate independently, there are many things that cannot work, right? The messages that these decays exchange with each other might get lost. They might not arrive at all, or they might arrive in the wrong order. Maybe I sent a message that's actually slow and arrives after a subsequent one is sent. Or maybe they can arrive more than once. We've seen this is also a possibility. And at the end of the day, here we're at the mercy of the network, and we have to kind of protect ourselves and do something about it. So we've established what the goal is, what the objective is. How do we get there? Now, the great thing here is that the properties that we just discussed, we can get them for free. We can get them for free if the structures that we use to model our state meet certain conditions. And there are exactly 3 rules that our CRDT have to comply with. And here's where things start to get a little bit more complicated, but still very, very simple. So know what is. So the first one is that all of the possible states of our CRDT must form what's called a partial order. We're going to be seeing what that means in a second, but the intuition is pretty simple, right? There needs to be a binary relation that, given 2 states, can tell me how to put them in order, right? You can tell me which one is bigger or if they're equal. And this property is going to let us talk about what's called a joint semilattice. And we'll see exactly what this is in a second. Second rule that we have to follow is that if we have an initial state S and we have an update U, the new state that gets produced as a consequence of U needs to be bigger or equal than the initial state. And bigger or equal I'm using it a little bit freely, but like the intuition should be clear, but really what this means is determined by the relation that we defined in the order that we just introduced. And the last rule is that when we have two states, S1 and S2, and we put them together, the new state that gets produced is the upper bound of S1 and S2. So 3 rules. Let's try to clarify exactly what this means. First thing that we want to understand is, what's an order? Like an order is a pretty simple thing, but if we want to formalize it correctly, we need to be a little bit careful. But an order is nothing more than 2 things. A set, S, so a collection of elements, so it could be the people in this room today, or it could be the integers between 5 and 10. And second thing is a relation between the elements of the set, right? So for example, it could be, if we pick integers, it could be the relation of greater than or equal to. There's 2 examples here. The one on the left is the one we just discussed, integers between 5 and 10. And if I take any 2 random elements in the set, I can always say which one is bigger or if they're equal. I can always put them in order. So this is a total order. There's a relation that exists for every pair of elements. The one on the right is a little bit different. In this case, the relation is a geographic one. So is this located in relation? So for example, Brooklyn is contained in New York City, that's contained in the US. But if I take New York City and Mumbai, how do I put them in order? Which one is located in the other one? I cannot do that, right? I cannot do that with this set and this relation. And this is a partial order, so something that's weaker than the other one. There are elements in it that I cannot compare. And if we extend this example a little bit, if we add a new element to the top of the set, Earth, now Earth as an element of this set is the upper bound of the set, because it's greater than or equal to every other element in the set. And in this case, what that means is simply defined by the relation that we introduced as an order. So it means geographically located in. And now that we defined these things, if we take 2 elements of the set, like New York and Seattle, the join of these 2 elements, is the smallest element of the set that's bigger or equal than both. And I'm, again, using bigger and equal a little bit freely, but the intuitively, it should be pretty clear. So if we take Mumbai and India, the join is India itself. And if we take instead Bronx and Delhi, we have to go all the way to the top in order to find the join, because that's the smallest element that satisfies the conditions. Okay, so we've defined all this. Now, a partial order in which every pair of elements has a join, you can probably guess at this point, is called a join semilattice. And the last piece of the puzzle that is simply the rules that join has to follow. It has to satisfy, and there's 3 of them. And we've seen this a few times already. Shouldn't be surprising to anybody, but the first one here is commutativity. So this is one that we probably all remember from school. So the order in which we join elements is relevant. I can do A join B, and that should be the same as B join A, has to be the same. Associativity, so this is, it doesn't really matter where I put the brackets. I can remove them. We can accumulate results intermediately as we please. That's very powerful as well. And finally, idempotency, this is also pretty simple. If I have a function and I apply it once or twice or multiple times, I get to the same end result. So it could be like, for example, the absolute value of an integer. Okay, so 3 properties. So at this point, we've kind of gone quite deep. We've seen like the precise structures of this data, the properties that we get by using them. We have to kind of like in Google Maps, zoom back and kind of go back to the level of abstractions that we had at the beginning. And if we remember, a few slides ago, we introduced what was our goal, our objective, strong eventual consistency. With the caveat that we have to consider all of the problems that we discussed, all the things that can go wrong. And the great thing about all of this stuff is that we can simply forget about all these problems. We can ignore them altogether like they don't exist. And we can ignore the fact that messages can be sent more than once. It doesn't really matter anymore. We can ignore that messages can arrive in the wrong order, and we can ignore that they can get lost along the way. And being able to ignore all of these problems is an enormous advantage when it comes to architecting and building software of this kind. And if you remember a few slides ago when we were talking about taking the max of 2 states, really what we were doing, I kind of lied at that point, but what we were doing really there was taking the join of the 2 states, right? And joining 2 states sometimes is as simple as taking the max, if we're talking about a simple counter, but sometimes for more complex structures, we have to be a little bit more careful in how we structure things. Okay, so last couple of slides. So at this point, let's zoom out, and we can go back to the initial problem that we had with the BBC. So at this point, synchronizing state across the nodes of our system becomes a much easier and tractable problem. And it does it exactly because the state that we use to model our state, the structure that we use to model our state, are CRDTs. And the CRDTs, they let us forget about all of the problems that would otherwise be either impossible or extremely expensive to solve. Stuff like, exactly once delivery, which is super tricky to get in practice. And there's a lot of companies out there that use CRDT in production for different use cases. Apple uses them for their note-taking application. So I can take notes offline if I'm on a plane, and then they will eventually synchronize perfectly with other devices. Atom, the text editor, they use CRDTs for letting programmers work on the same file in real time from different machines. The game League of Legends, they use like a NoSQL database called React, I think, for their in-game chat system that has like millions of active users. And there's many more. And we've seen how these things can be a little bit scary at the beginning, but once we understand and we have just a few rules to comply with, then we get in exchange these incredible properties. And this is all I have for you today. Thank you very much.
All right, so let's open the floor for some questions here. Do we have any from the crowd? Well, I do have some from the ones written out. So, of course, if you remember, you can always send them through the links on the badge. So I have some from there. So the first question is, what programming language did you use to build this?
So we have 4 different implementations this. They run in different environments. There's one in Scala, one in TypeScript that runs in the browsers, one that's in Haskell for like reference, and we're building now one that's in Kotlin multi-platform to run on iOS and Android natively, as well as on the server via, basically in Scala.
Is the state model that you've built open source?
Not right now. I'm hoping that in the future it will be open source, because the great thing about the model is that it's really generic. It's not specific to our use case or anything similar. It can be used for other use cases as well. So I'm hoping that in one or 2 years' time we'll be able to make it open source and other people can use it and get benefits.
All right, so that's all that I have on here. I'll give you one more chance in the crowd. Awesome. Here you go.
Thank you very much for the talk. Yeah, I have a question because I see the benefits when using like data types like accumulators or counters. But for example, when the data is not doesn't have this order relation, like for example, temperature changes in a room, like you need an extra information or meta information, like maybe the timestamp, I guess. And then the join function will have to use that timestamp as the order.
Yeah, I mean, this is a fair point. Like the example I used was pretty simple, and that's like just a counter. There's more complex structures. If you introduce like a time element, if you have like time window, then you have to communicate more information, like a timestamp of the events, for example, or even more complex things. But yeah, that's a fair point, absolutely.
All right, so then that's going to be it for us today. Let's give Marco another round of applause.